In the universe, there's a whole wide range of different objects that can exist, from asteroids to gargantuan black holes. They may seem incredibly different from the outset, but really speaking, there's only one key difference that the universe cares about. It's mass. So to see how mass changes the properties and type of object, we'll start with the very smallest thing and work our way up to the very largest thing. And in this video, I'll be talking with scientific notation. That means if I say a number 10 to the power of 20, say, that means that there's a 1 followed by 20 zeros. So just keep that in mind, because we're going to be dealing with some absolutely enormous numbers. So we might as well start with the smallest objects in space, little micrometeors. These are just effectively pebbles zooming around space. Not too much interesting going on. So let's take many thousands upon thousands of kilograms and start dumping them onto this micrometeor, making it bigger and bigger. Well, if we took 10 to the power of 20 kilograms of material and put it onto this little asteroid, it would grow to be something a little more interesting. Its size would be about 600 kilometers across, and it will have formed what we call a minor planet, or a dwarf planet. Now, the reason it's become spherical is because there's so much material there now and so much gravity, it's pulled all of the material into the kind of lowest energy state, because nature is very lazy and always wants to find the lowest energy state. So in this case, it's a sphere, and this type of state is known as hydrostatic equilibrium. So in this sphere, we have a minor planet. Now, if you add, say, 10 times the amount of mass, so now we have 10 to the power of 21 kilograms, you'll have something that weighs as much as the largest object inside of the main asteroid belt, Ceres. That's around about 10 to the power of 21 kilograms. So it's reasonably heavy, certainly the heaviest of all the asteroids, and has earned itself a place as a dwarf planet. If we were to go look at the far extent of the solar system to the most well-known dwarf planet, Pluto would need to add 100 more kilograms, so it's 10 to the power of 22 kilograms as the mass of Pluto. So when you get to this mass, you have some potentially interesting things going on. The object is now large enough to pull itself into a sphere, and it's now large enough to retain thin bits of atmosphere like we can see around Pluto. But these objects aren't planets, despite what some people might say. So how heavy is a planet? Well, if you take 10 Plutos, shove them together, you'll have something that's as massive as Mercury, the smallest planet in the solar system. And if you took 10 Mercuries and slammed them together, you would have enough mass to make effectively one Earth. So Earth is about 100 times more massive than Pluto. So we've stepped up the mass scale quite a lot. And on Earth-sized planets, you can have lots of interesting things. You can have atmospheres being retained, say, with the case of Earth, and with Venus, which is about the same mass. But it's not so much atmosphere that you can't see the surface. So rocky planets like Earth, Venus, Mercury, and Mars are called terrestrial planets. There's a terrestrial surface that you could walk around on if you so desired. But this isn't the limit of as far as planets can go. If you took Earth and you took another Earth and you slammed them together to make perhaps some kind of super Earth, twice the mass of Earth, suddenly something new can happen. This object, this super Earth, now has enough gravitational pull to actually hold on to the most volatile of gases, hydrogen and helium. So instead of escaping the atmosphere like they do on the Earth, they can be trapped by the gravitational potential of that planet. And suddenly, these bigger objects can access a lot more mass of the universe, since about 99% of the entire universe is these very light atoms. There's a lot of stuff that they can pick up, and they'll become something known as an ice giant. We have examples of ice giants in our solar system with Uranus and Neptune, which are both about 10 times more massive than the Earth. But this again isn't the limit for as big as planets go. You can make planets even bigger still. Say Saturn, for example. That's around 5 times more massive than Neptune. And bigger yet is Jupiter, the largest planet in our solar system. And that's about 3 times more massive than Saturn. So massive you could put all of the other stuff that's not included in the Sun together, and Jupiter would still weigh about 2 times more than that. So we had 3 different distinctions for what a planet could be. We could have a terrestrial planet, one with a rocky surface. We could have an ice giant, a fairly gaseous planet with a solid core. Or we could have a gas giant, a very large gaseous planet with perhaps a solid core, perhaps not. Now, all of these planets are fundamentally different from the Sun in that they don't produce their own light at the center of themselves. To do this, they need to have enough mass to force nuclear fusion to happen at the center. And the planets don't have that. So the line between something being a planet and becoming a star is a line at about 13 times the mass of Jupiter when something becomes known as a brown dwarf. Now, brown dwarfs don't necessarily do fusion the same way as the Sun does fusion in the center, but it is possible for fusion to occur in the center of a brown dwarf. But if you want to actually get to a star, you need to go bigger still. You need about 100 times the mass of Jupiter to make what's called an M-dwarf star. Now, these are the smallest possible stars that you could make, and they're small in many respects. Although they've got 100 times the mass of Jupiter, to reach hydrostatic equilibrium, their size is actually on the order same size as Jupiter. But right down in the center of this M-dwarf, fusion is occurring, producing energy out of slamming atoms together. So it is a star in its own right. If we wanted to grow even further and become a Sun-like star, you would need to add 10 of these M-dwarf stars together to make a Sun-like star. The mass of the Sun is about 10 to the power of 30 kilograms, so that's a 1 followed by 30 zeros. It's a completely wild number. It's 1,000,000 times more massive than the Earth, and pretty much completely unfathomable to our poor little brains. But this enormous number isn't as far as stars can go. The Sun is a pretty run-of-the-mill star. In fact, there are stars that can be much bigger still. Our Sun will die by puffing off all of its outer layers, leaving a white dwarf behind, which weighs about the same as what the Sun would. But if you have a star that's 8 times more massive than the Sun, or even more, you can explode the star and create things like neutron stars, or perhaps collapse it directly into black holes. So what is the most massive star that's known? The most massive star known is R136A1, and it's 315 times the mass of the Sun. Now, this absolutely enormous star will lose a lot of its mass through its lifetime, but it will still blow itself up in the end. So stars can get incredibly massive, so this is 100 million times more massive than the Earth. But I mentioned before things like neutron stars and black holes. These too are very massive objects. A neutron star would weigh around about the mass of the Sun, but it's compressed to an incredibly small area, the size of about 15 kilometers across, or the size of an average city. But these are kind of limited in how big they can get, because eventually if you put too much material onto a neutron star, this hydrostatic equilibrium, this pressure between particles working against gravity, won't work anymore. It will just collapse down to make a black hole. So if you took enough mass and you crammed it into a small enough space, you'll make a black hole. So stars blowing up can make black holes that are around, say, 10 solar masses, 10 times the mass of the Sun. So these are pretty small as far as black holes go. But I'm sure many of you have heard about the supermassive black holes that live at the center of galaxies. At the center of our galaxy, there's something called Sagittarius A star, which is believed to be a supermassive black hole, and it has about 2.6 million times the mass of the Sun, so this object is absolutely gargantuan, and again packed into a relatively small area for its mass. But how big can black holes get? Well, there's really no limit to it. If you take a big black hole and you smash it together with another big black hole, you'll make an even bigger black hole and produce some gravitational waves. The largest black hole that we know of today is in the center of the galaxy Holm 15A, and it's been measured to have a mass about 40 billion times more massive than our Sun. So that's an incredibly large number, and it's believed to have reached this enormous mass just by slamming lots of massive black holes together. So one prediction is that there might have been about 8 galaxies that emerged with this one big galaxy in the past. Each one of those mergers would have had the black holes collide together and produce an even more massive black hole. So going from the very smallest thing, asteroids, all the way up to the biggest things with black holes, the only distinction really is mass. You could turn an asteroid into any one of those objects, into a terrestrial planet, an ice giant, a gas giant, a star, or even a black hole if you just added enough mass to it. And the universe certainly has enough mass to go around for all of these different wonderful things.